Göttingen, a city with great scientific tradition. This spring, celebrations will begin here to mark 100 years of quantum physics. Even 100 years ago, Göttingen was a center of physics. Here, one man revolutionized our understanding of quantum mechanics, Max Born. Born's groundbreaking interpretation of quantum physics turned the prevailing worldview upside down. Instead of clear causal relationships, probabilities now determined the state of nature. For a long time, physics was considered nearly complete, but suddenly fundamental questions arose again and revolutionary developments became possible. But who was Max Born and why is his legacy so significant? Quantum mechanics describes the world of smallest particles, atoms, electrons and photons. Unlike in classical physics, these particles do not simply move like tiny billiard balls on predictable paths. Instead, they behave sometimes like particles and sometimes like waves. Their exact location or state cannot be precisely predicted, only their probability of being in a certain place. One of the central achievements of quantum physics was the so-called Born rule. It states that we cannot directly read from a particle's wave function where it is located, but we can calculate how likely it is to find the particle at a specific position. Mathematically, this means that the probability is given by the square of the wave function's absolute value. This rule remains a fundamental principle of quantum mechanics today and is crucial for our understanding of quantum computers, semiconductors and many modern technologies.
Die Born'sche Regel ist die entscheidende Verbindung von Theorie und Experiment. Es ist das, was aus der Quantenmechanik tatsächlich eine verifizierbare Theorie macht. Die Born'sche Regel beschreibt, mit welcher Wahrscheinlichkeit wir eine bestimmte Beobachtung machen in einem Experiment. Also ganz im Gegensatz zur klassischen Mechanik, wo wir wissen, etwas passiert oder es passiert nicht, kann die Quantenmechanik ganz prinzipiell nur die Aussage machen, etwas passiert mit einer bestimmten Wahrscheinlichkeit.
A simple illustration of Born's rule is possible using the double slit experiment. The double slit experiment demonstrates this concept impressively. When individual particles are shot through two slits onto a screen, they do not simply land in two distinct areas. Instead, an interference pattern emerges, just as if the waves were overlapping. This is because the wave function splits at the slits and the probabilities of different paths interfere. Where two peaks overlap, the probability of finding a particle is highest. This experiment vividly shows that quantum mechanics does not predict single outcomes, but only probabilities of different possibilities. At the beginning of the 20th century, Göttingen became the epicenter of a scientific revolution, and one man stood at its center, Max Born. Born was born in 1882 in Breslau and was a brilliant mathematician and physicist. In Göttingen, he became professor and began shaping a new understanding of quantum mechanics.
Es gibt also von ihm aus dem Jahr 1924 eine Arbeit, wo dann auch zum ersten Mal das Wort Quantenmechanik auftaucht. Also der Titel ist, glaube ich, zur Quantenmechanik. Und neben dem Wissenschaftlichen ist, denke ich, ein weiterer wichtiger Punkt, dass Max Born ein sehr guter Lehrer war und auch seine Arbeitsgruppe sehr unterstützt und gefördert hat.
But Born was not just a brilliant theorist, he was also an exceptional teacher. Under his guidance, some of the greatest minds in physics gathered in Göttingen. Werner Heisenberg, Wolfgang Pauli, Maria Goeppert-Mayer, Enrico Fermi and Robert Oppenheimer, scientists who would later shape the physics of the 20th century. In 1933, everything changed for Max Born. When the Nazis came to power, he lost his professorship in Göttingen because he was Jewish and was forced to leave Germany, like many other great scientists of the time. Born found refuge in Cambridge and later in Edinburgh. Despite being in exile, he continued his research, contributing significantly to solid-state physics and the statistical interpretation of quantum mechanics. In 1954, Born's contributions to quantum mechanics were officially recognized when he was awarded the Nobel Prize in Physics. However, he only returned to Germany after his retirement. He spent his final years in Bad Pyrmont, where he wrote about science and responsibility, warning against the dangers of nuclear weapons, weapons that some of his former students had helped develop. Max Born died in 1970. His name may not be as well known as those of his students, but his ideas continue to shape physics to this day.
Also Sie können keinen Halbleiter verstehen ohne Quantenmechanik. Also sobald Sie dann, was weiß ich, die Stromspannungskennlinien gemessen haben, dann brauchen Sie keine Quantenmechanik mehr. Aber wenn Sie wissen wollen, wo das tatsächlich herkommt, dann brauchen Sie Quantenmechanik. Sie können auch keine Solarzelle verstehen ohne Quantenmechanik. Ja, das sind alles die zugrunde liegenden Prozesse, sind alles quantenmechanische Prozesse.
Quantum physics often seem abstract, but without it, our world would be completely different. Computers, smartphones, GPS, and modern medicine. All of these technologies are based on the principles that Born and his students developed nearly a century ago. And the journey is far from over. Quantum computers, new materials, and revolutionary sensors. The next generation of quantum physics is just beginning. Max Born helped us understand the quantum world, and his legacy continues to influence every facet of modern technology. The physics of the past is the future of today. And who knows, maybe right here in Göttingen, the next groundbreaking discoveries will be made.